This survey on fairness-aware recommender systems is a comprehensive overview of the current advancements in enhancing fairness in recommendation scenarios. The paper discusses the importance of fairness, its various interpretations, and its impact on both users and item providers. It highlights the negative societal impacts caused by unfairness in recommender systems, such as gender discrimination in job recommendations and geographic imbalance in MOOC course recommendations. The survey provides a detailed taxonomy of fairness concepts and formulations, categorizing them into pre-processing, in-processing, and post-processing methods. It also explores the connection between fairness and other principles of trustworthy recommender systems, including explainability, robustness, privacy, and more. Furthermore, the paper discusses the significant influence of fairness-aware recommender systems on real-world industrial applications, such as e-commerce, education, and social activities. The authors emphasize that fairness is crucial for enhancing the trustworthiness of AI services, as it promotes equal opportunities and reduces biases. They introduce various datasets and evaluation metrics used in literature exploring fairness in recommender systems, which can be utilized to assess the fairness of these systems. The paper concludes by discussing the promising opportunities in comprehending concepts, frameworks, the balance between accuracy and fairness, and the ties with trustworthiness, ultimately aiming to foster the development of fairness-aware recommender systems. This survey delves into the realm of fairness-aware recommender systems, providing a comprehensive overview of the concepts, frameworks, trade-offs, and trustworthiness within these systems. It begins by discussing the lifecycle of a recommender system, which includes data collection, model learning, and feedback phases. The authors then categorize causes of unfairness in these systems into three categories: data bias, model bias, and feedback bias. Data bias can arise from user attributes such as age, gender, geographical location, and profession, which may lead to biased recommendation results. For instance, a music recommender system may recommend hip-hop music to younger users, while a user from this age group might be interested in exploring different genres. Similarly, gender and geographical location can also influence recommendations in certain contexts. User selection bias is another form of data bias, occurring when users select items based on their preferences and behavior. This can result in inconsistencies between user preferences and behavior records. For example, in a music streaming media recommender system, explicit feedback such as ratings of items can be affected by user feedback bias, leading to incorrect assumptions about user preferences. Exposure bias occurs when users only have access to a portion of the available item set. This bias is often present in implicit feedback data, which refers to whether the user interacts with the item. In e-commerce sites, users may provide feedback on recommended items by searching and browsing various product pages, but their browsing behaviors may contain incorrect clicks, leading to unfair recommendations. The authors also introduce fairness as a concept originating from sociology, economics, and law, requiring that recommender systems treat all users and items equally. They discuss how unfairness can be eliminated from systems, and present common fairness expressions that can measure the existence of bias. In conclusion, this survey provides a holistic taxonomy for fairness-aware RS methods, highlighting the importance of considering fairness in the development of trustworthy recommendation systems. It encourages researchers to think about the ethical dimensions of their systems, including fairness, explainability, and robustness, and emphasizes the need for a more comprehensive understanding of the relationship between fairness and other ethical principles. In the lifecycle of recommender systems, biases can emerge in various phases, including data collection, model learning, and feedback loop. These biases may result in unfairness phenomena that affect the quality of recommendations. For instance, popularity bias amplifies the recommendation of popular items, while feedback bias can lead to the continuous reinforcement of these biases over time. Time bias also occurs when new items are overrepresented, leading to a lack of consideration for long-term user interests. To address these issues, fairness-aware recommender systems have been developed. Fairness expressions in these systems include individual fairness, group fairness, single-sided fairness, multi-sided fairness, and ranking fairness. Individual fairness focuses on maintaining the interests of a single role, such as ensuring that users receive fair recommendations. Group fairness, on the other hand, aims to maintain the interests of multiple roles, including both consumers and suppliers. Multi-sided fairness strives to balance the exposure of items across different aspects and ensure proportional exposure of both groups relative to their average utility. Static fairness is defined as providing a short-term fair recommender system, regardless of changes in the recommendation environment. In contrast, dynamic fairness considers dynamic factors in the environment to maintain fairness. For example, dynamic fairness may recommend an item that was recommended a long time ago with the same probability as an item recommended recently. Ranking fairness ensures that the proportion of protected individuals appearing within a ranking prefix exceeds a predetermined threshold. This perspective asks that similar items or groups of items receive equal opportunities for exposure in the recommendation list. To mitigate these biases and ensure fairness, various methods have been proposed, such as using prior knowledge from warm start recommendations to train cold start recommender systems, and employing fairness constraints in the loss function of the model to reduce bias. However, solving the cold start problem is challenging due to the lack of sufficient data on user behaviors or item attributes. The dynamic fairness granularity for recommender systems can be adjusted by a slack factor, which is used to balance the fairness of both consumers and suppliers. Fairness-aware recommender systems encompass various stages, including preprocessing, in-processing, and post-processing. In the preprocessing stage, fairness-enhancing methods are employed to mitigate biases in the training datasets. These biases can be amplified throughout the lifecycle of a recommender system, resulting in unfair recommendations for users. Data relabeling, resampling, and modification are three categories of fairness-aware preprocessing methods. Data relabeling involves changing labels to remove biases in the input data. For instance, Wang et al. Designed a self-supervised relabeling framework to mitigate noise in implicit feedback. Data resampling ensures uniform sampling to avoid distributional biases. Montanari et al. Proposed a uniform sampling algorithm to reduce the dataset size. Data modification involves augmenting or modifying biased data to reduce bias. Wang et al. Implemented natural language processing preprocessing techniques to modify training data in crowd testing recommendation. In-processing methods improve fairness from a method perspective. Regularization-based methods, causal inference-based methods, adversarial learning-based methods, reinforcement learning-based methods, and ranking optimization-based methods are employed in this stage. For example, Clover uses regularization to address cold start bias in cold start recommender systems. Post-processing methods treat the model as a black box and solely process the model's output results. Non-parametric re-ranking methods and parametric re-ranking methods are employed in this stage. Zheng, a non-parametric method, addresses exposure bias in cold start recommender systems. Hyperfair, a parametric method, addresses exposure bias in general recommender systems. Fairness concepts, such as individual fairness, equal opportunity, causal fairness, long-term fairness, and envy-freeness fairness, are also discussed. Causal fairness considers observational data and incorporates additional causal relationships within them. Long-term fairness is affected by time and considers the long-term impact of fairness interventions. Envy-freeness fairness states that each user should prefer their own recommendations over those of other users. This survey delves into fairness-aware methods in recommender systems, focusing on the elimination of bias and unfairness through various techniques. In processing fairness methods, such as regularization, causal inference, adversarial learning, reinforcement learning, and ranking methods, are discussed in detail. Regularization-based methods, for instance, employ norm-based, matrix-based, and correlation-based regularization terms to alleviate different types of bias, including user-oriented bias, popularity bias, and group bias. These regularization terms can be added to the main loss function to penalize the model for predicting unfairness. Causal inference for fairness, on the other hand, explores the causal relationships between variables in a recommender system, utilizing techniques like inverse propensity scoring, backdoor adjustment, and counterfactual inference to mitigate unfairness. For example, inverse propensity scoring reweights samples to reduce the influence of biased samples without altering the causal relationship between variables. These methods are crucial for creating a more equitable and transparent recommendation process. A survey on fairness-aware recommender systems. Fairness-aware recommender systems aim to ensure that recommendations are unbiased and equitable. To achieve this, various methods have been proposed, including propensity score methods, backdoor adjustment, and counterfactual inference. Propensity score methods, such as IPS, adjust the recommendation scores based on the propensity of users to interact with items. Backdoor adjustment methods, like DECRS, remove unfairness by blocking relationships that lead to biases. Counterfactual inference methods, including MACR, transform the real-world causal graph into a counterfactual graph to alleviate biases. Adversarial learning, as in FairTED, involves a generator and discriminator to remove sensitive attributes. Reinforcement learning, such as Zhang et al.'s fairness-constrained CMDP, models the recommendation process as a constrained Markov decision process to ensure dynamic fairness. These methods address various aspects of fairness, including exposure bias, popularity bias, and time bias, to provide more equitable recommendations. Here is a combined summary of pages 13 and 14 of the research paper. Fairness-aware recommender systems employ various techniques to mitigate biases and ensure equitable treatment of users and items. One such approach is reinforcement learning, which involves dynamically maintaining the trade-off between accuracy and fairness. For instance, FairRec uses reinforcement learning to generate recommendations by combining user preferences with system fairness. Another approach is multi-objective reinforcement learning, which involves creating a fairness-aware recommendation framework that introduces conditional networks and modifies them according to user preferences. Ranking optimization for fairness is another crucial aspect of fairness-aware recommender systems. This involves employing unbiased loss functions to reduce unfairness in recommender systems. There are two types of ranking losses commonly used in learnable recommender systems: pointwise loss and pairwise loss. Pointwise loss, such as binary cross-entropy, BCE, and mean-squared error, MSE, minimizes the difference between the calculated recommendation score and the ground truth to capture user preferences for individual items. Pairwise loss, such as Bayesian personalized ranking, BPR, maximizes the user preference gap between the observed items and the unobserved items. However, the BPR loss can be affected by popularity bias and exposure bias, leading to unfair outcomes. To address this, Wang et al. Propose a cross-pairwise ranking loss, CPR, for unbiased training. The CPR loss uses cross-pairwise interactions as training samples and decomposes exposure probabilities of items into user-specific, item-specific propensity, and user-item relevance, which are not independent of each other and thus contain bias. In addition to these methods, there are other approaches to enhance fairness in recommender systems, such as analyzing the flaws of BPR loss and adding regularization terms to achieve unbiased ranking. Post-processing methods, including re-ranking methods, can also be used to enhance fairness in recommender systems. These methods aim to rearrange the recommendation results provided by target models, without repeating the manual re-ranking. Re-ranking methods can be categorized into non-parametric re-ranking and parametric re-ranking, depending on whether a parameter learning process is required to conduct re-ranking. Non-parametric re-ranking methods represent learning-free algorithms to conduct re-ranking concerning fairness, whereas parametric re-ranking methods require a parameter learning process to conduct re-ranking. This section of the paper focuses on fairness-aware recommender systems, specifically highlighting re-ranking methods and evaluation metrics for fairness. Re-ranking methods are categorized into two types: non-parametric and parametric. Non-parametric methods, such as score scaling models, convert the recommendation optimization problem into AO1 integer programming and knapsack problem, employing greedy algorithms or solvers to perform re-ranking. Parametric re-ranking methods, on the other hand, require a learning process to improve fairness during the post-processing stage. These methods have better debiasing ability and are more competent when enhancing equality opportunity-based fairness. In terms of evaluation, the authors discuss the importance of using various datasets to detect unfairness in recommender systems and evaluate fairness-enhancing methods. They present a summary of commonly used datasets, including Amazon, Beauty, Opinion, Last.fm, Movie Lens, Yahoo R3, and Yelp, each with its basic information and possible scenarios for addressing different bias issues. For evaluation metrics, the authors differentiate between accuracy metrics and fairness metrics. Accuracy metrics include area under curve, AUC, precision, recall, average precision, AP, and normalized discounted cumulative gain, NDCG at K. Fairness metrics, on the other hand, include the Gini coefficient, which measures value inequality, and KL divergence, which computes the divergence between two distributions and can be used to measure various biases, such as popularity bias. The survey on fairness-aware recommender systems emphasizes the importance of ensuring that recommendation results are fair. It discusses various metrics and methods to evaluate fairness, including KL divergence, strictness parameters, and measures such as mean, median, variance, skew, and kurtosis. The paper highlights the impact of fairness-aware recommender systems on real-world situations, including e-commerce, education, and social activities. In e-commerce, for instance, the Scenario-Aware Ranking Network, SARNet, is designed to mitigate data bias. In education, re-ranking approaches ensure that each group receives the expected exposure. The paper also explores fairness in job and news recommendations, addressing biases such as exposure bias, user bias, and popularity bias. For instance, in job recommendations, the inverse propensity weighting method is used to reduce bias. In news recommendations, ProFairRec prioritizes provider fairness through adversarial learning. The survey concludes by discussing fairness in streaming media recommendations, including music and video recommendations, highlighting the need for transparency and fairness to artists. Fairness-aware recommender systems aim to ensure that outcomes are unbiased and equitable, adhering to principles like equal opportunity and population parity. A large-scale deployment of a fairness framework in LinkedIn Recruiter has the potential to positively impact over 630 million members. Adversarial learning can be used to reduce bias arising from user-sensitive attributes, and KL divergence can capture less candidate-aware bias. Trustworthy recommender systems are crucial, as they can inspire user confidence and avoid legal issues. Trustworthiness is evaluated based on 4 ethical principles: explainability, robustness, privacy, and fairness. Explainability requires that the decision-making process and input-output relationships of recommender systems be logically explained. However, most current models operate as black boxes, leading to user distrust. Robustness refers to the ability to operate normally when threatened or attacked, ensuring safety, reliability, and robustness in handling errors or inconsistencies. Privacy requires protecting personal data and preventing unlawful discrimination. Fairness is connected to other trustworthy dimensions. For instance, methods mitigating fairness issues can also enhance explainability. Causal inference analyzes the causes of bias and provides explanations for the decision-making process. Counterfactual reasoning can promote both explainability and fairness. Connections with robustness involve constructing antidote data to mitigate data bias, making the model more robust. Fairness is also linked to privacy, as training data may contain user-sensitive attributes that must be protected. Some works establish a connection between fairness and privacy, ensuring that user-private information is not used extensively for personalization. Table 4 outlines the connections between fairness and other trustworthiness properties, including explainability, robustness, privacy, and discrimination. Various methodologies are presented, such as causal inference, data modification, regularization, re-ranking, and others. These connections are crucial in developing trustworthy recommender systems that ensure fairness, explainability, robustness, and privacy. This paper presents a comprehensive survey on fairness-aware recommender systems, focusing on the challenges and opportunities for future research. It begins by introducing fundamental concepts related to recommender systems and fairness, then delves into different types of biases that cause unfairness at each stage of the system's lifecycle. The paper also explores various manifestations of fairness in different recommendation scenarios, paving the way for introducing subsequent methods. The authors discuss fairness-aware recommendation methods, categorizing them into 3 processing stages: pre-processing, in-processing, and post-processing. Each stage is detailed, highlighting the categories of methods and their implications. Furthermore, the paper introduces datasets suitable for different recommendation scenarios, providing insights into how these datasets can be utilized to evaluate the fairness of a recommender system. The paper concludes by outlining future directions for fairness-aware recommender systems, emphasizing the need for customized fairness concepts, general frameworks, trade-offs between fairness and performance, and mutual promotion with trustworthy properties. It highlights that most current works focus on the association between fairness and trustworthiness without improving explainability, and that future works should focus on the intrinsic interaction between fairness and other trustworthy properties in recommender systems. In addition, the paper emphasizes the importance of integrating fairness and other credible properties in a recommender system, establishing internal correlations between fairness and properties, reducing conflicts between properties, and building a credible recommender system. Table 6 illustrates the current state of research on integrating fairness methods and trustworthiness properties, revealing numerous unexplored areas such as applying reinforcement learning methodologies to develop explainability and fairness recommender systems. In the realm of machine learning and artificial intelligence, the concept of fairness has emerged as a crucial consideration in the development of recommender systems. These systems, designed to personalize content for users, can inadvertently perpetuate societal biases, leading to unfair outcomes. The survey on fairness-aware recommender systems presented in this paper aims to provide an overview of the current state of the art in fairness awareness, outlining various scenarios and fairness measurement metrics. The authors highlight the importance of fairness in e-commerce, education, and other areas closely related to people's lives. They emphasize the role of trustworthy properties, such as transparency, accountability, and privacy, in enhancing trust in fairness-aware recommender systems. Furthermore, they discuss future directions for fairness-aware recommender systems, including the development of fair and trustworthy systems. The paper also delves into the concept of fairness in job recommendation, with a focus on mitigating algorithmic bias. It presents various approaches to address this issue, including debiasing, fairness-aware regularization, and the use of fairness-aware learning methods. Moreover, the authors discuss the interplay between fairness and other trustworthy properties, such as privacy and transparency, in enhancing user trust in fairness-aware systems. In addition to discussing fairness in the context of recommendation, the paper explores the connection between fairness and other trustworthy properties, such as privacy and transparency. It highlights the need for a comprehensive understanding of these properties to ensure that fairness-aware recommender systems are not only fair but also trustworthy. The authors also emphasize the importance of auditing and evaluating fairness-aware systems to identify potential biases and limitations. The paper concludes by outlining the future directions for fairness-aware recommender systems, including the development of fair and trustworthy systems. It emphasizes the need for continuous research in this area to ensure that these systems promote fairness and trustworthiness, ultimately enhancing user satisfaction and trust in the recommendations provided. This section of the research paper focuses on fairness-aware recommender systems, encompassing various techniques to mitigate bias and ensure equitable exposure for users and items. The authors provide an extensive overview of different approaches to address fairness in recommendation, including fairness-aware ranking, learning to rank, and fairness-aware matrix factorization. They also discuss the importance of considering multiple fairness notions, such as demographic fairness, equal opportunity, and fairness of exposure. The paper highlights the significance of understanding the trade-offs between fairness and accuracy in recommendation. It emphasizes that achieving fairness often comes at the cost of accuracy, necessitating a balance between these two objectives. Moreover, it underscores the importance of considering the impact of data sampling on hyperparameter optimization in recommendation algorithms. The authors also explore the role of metalearning in enhancing fairness in recommendation. They discuss how incorporating fairness constraints into the learning process can lead to more equitable outcomes. Furthermore, they examine the use of causal reasoning to eliminate popularity bias and improve fairness in recommendation. The paper concludes by emphasizing the need for further research in fairness-aware recommendation systems, particularly in understanding the interplay between fairness and other aspects like diversity and privacy. It also suggests that future work should focus on developing more robust evaluation metrics for fairness and integrating fairness considerations into the design of recommendation algorithms. The paper provides a comprehensive survey on fairness-aware recommender systems, highlighting the importance of addressing various biases such as popularity bias, item under recommendation bias, and user attention bias. It discusses several approaches to mitigate these issues, including debiased candidate generation, fairness-aware tensor-based recommendation, and calibrated fast-fair federated recommendation systems. The survey also covers different evaluation metrics for fairness, such as the Fairness Index and the average relative change in exposure, which can help researchers and practitioners assess the effectiveness of their algorithms. The authors emphasize the need for fairness awareness in both the design and evaluation of recommender systems to ensure equitable exposure for all items. They present various techniques for bias mitigation, including contrastive learning, context bias-aware recommendation, and popularity opportunity bias reduction. Furthermore, they discuss the challenges of fairness-aware recommendation, including the trade-off between fairness and accuracy, and the need for more diverse and comprehensive datasets to evaluate fairness. In addition to the technical aspects, the paper touches upon ethical considerations, emphasizing that fairness is not a one-size-fits-all concept and may vary depending on the context and goals of the recommendation system. It also calls for further research on fairness-aware recommendation, particularly in the areas of dynamic fairness, fairness in sequential recommendation, and fairness in multi-stakeholder environments. Overall, the survey provides a thorough overview of the current state of fairness-aware recommender systems, highlighting key challenges, methodologies, and future directions in this rapidly evolving field.